On the evening of December 23, 1944, in a secure laboratory at the Army High Command's weapons testing facility near Kummersdorf, south of Berlin, Dr. Engineer Hermann Riegner bent over a disassembled American artillery shell. The nose assembly lay on the examination table under bright overhead lights. Inside that nose was something that should not exist. Riegner had spent the previous 2 hours carefully removing the fuse assembly from its housing. His hands moved with precision despite the cold that seeped through the walls. The building had minimal heating. Fuel was reserved for military operations, not research laboratories examining captured equipment. But the cold was the least of Riegner's concerns. What troubled him was the object on the table. The fuse was small, roughly the size of a large beer bottle. It weighed just under 2 pounds. Inside the aluminum casing were 5 miniature vacuum tubes, each smaller than his thumb. There were capacitors, resistors, a battery system, safety mechanisms, and what appeared to be a complete radio transmitter and receiver circuit, all packed into a space barely larger than his fist. Riegner understood immediately what this device was supposed to do. The Americans had built a proximity fuse, a shell that could sense its own distance from a target and detonate automatically in mid-air. The concept was not new. Germany had been researching proximity fuses since the early 1930s. Rheinmetall Borsig had prototypes. Telefunken had working models. Multiple research teams across the Reich had explored acoustic detection, electrostatic field sensing, and radio frequency systems. Every approach had failed for the same fundamental reason. The engineering was impossible. To work in an artillery shell, an electronic fuse needed to survive forces that destroyed conventional electronics instantly. When fired from a standard field artillery piece, a shell accelerated from 0 to more than 2,000 feet per second in less than 1/10 of a second. That created acceleration forces exceeding 20,000 times the force of gravity. Simultaneously, the rifling grooves in the gun barrel spun the shell at 25,000 revolutions per minute to stabilize its flight. Any vacuum tube subjected to those forces would shatter. The glass envelope would crack, the filament would break, the internal elements would tear loose and destroy the circuit. German scientists had tested hundreds of vacuum tube designs. Every single one failed when subjected to artillery acceleration. The tubes that survived the initial shock broke apart from centrifugal forces during flight. The tubes that survived flight had circuit failures from microphonic vibrations. There was no solution. German research teams had concluded by 1943 that proximity fuses using vacuum tubes were technologically impossible. The physics simply did not permit it. Yet here on Riegner's examination table was proof that someone had solved the impossible problem. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Riegner pulled one of the miniature tubes from the circuit board and held it up to the light. The glass envelope was intact despite the shell having been fired from an American artillery piece, having flown several thousand meters through the air while spinning at 25,000 revolutions per minute and having impacted the ground at terminal velocity without detonating. The tube had survived. He placed it under a magnifying lens and examined the internal structure. The filament was still connected. The grid wires were still properly positioned. The tube showed no signs of internal damage. This should not be possible. Riegner set the tube down carefully and picked up the circuit board. The components were miniaturized beyond anything he had seen in German electronics. The resistors were half the size of standard military-grade components. The capacitors were custom designed for minimal space. The entire transmitter-receiver circuit was smaller than a deck of playing cards. He understood why the Americans had succeeded where Germany had failed. This was not a question of scientific knowledge or theoretical understanding. Both nations had brilliant physicists. Both nations understood radio principles. Both nations had explored the same technical approaches. The difference was manufacturing capability and engineering persistence. The Americans had developed vacuum tubes that could withstand forces German engineers had declared impossible. They had miniaturized electronics to degrees German industry could not match. They had solved thousands of small engineering problems that German research teams had abandoned as unsolvable, and they had done this in secrecy so complete that German intelligence had not detected the program despite 3 years of Allied combat operations using proximity fuses at sea. Regner wrote his initial assessment in clear, direct language. The American proximity fuse represented a breakthrough in applied electronics and manufacturing precision. The device demonstrated capabilities that exceeded German technological assumptions. Most critically, the existence of this technology called into question fundamental assessments about what was technically feasible in 1944. If the Americans could manufacture vacuum tubes that survived 20,000 G-forces, what else had they achieved that German scientists had declared impossible? The assessment went to the Army High Command on December 24th, Christmas Eve. Nobody read it that day. German forces were retreating across Belgium. American armies were counterattacking at Bastogne. The Eastern Front was collapsing. Reich Marshal Hermann Göring was preparing to meet with Adolf Hitler at the Führer's headquarters in the West. Strategic decisions about the future conduct of the war dominated every conversation at High Command. A technical report about a captured artillery fuse was filed away for later review. But the story of how that fuse came to exist begins 4 years earlier, on the other side of the Atlantic Ocean, in a laboratory in Washington, where a physicist named Merle Tuve was about to receive an impossible assignment from the United States Navy. On August 12, 1940, Captain Harold Bowen of the Navy Bureau of Ordnance walked into the offices of the National Defense Research Committee in Washington with a request that most scientists would have considered impossible. The Navy needed a proximity fuse for anti-aircraft shells. They needed it to work reliably in combat conditions. They needed it to be safe enough that sailors could handle it without specialized training. They needed it to be cheap enough to manufacture by the millions, and they needed it within 2 years. The problem was urgent and existential. At Pearl Harbor, 9 months later, on December 7, 1941, Japanese aircraft would attack the naval base with devastating effectiveness. American anti-aircraft guns would fire thousands of shells equipped with timed fuses. These fuses were supposed to detonate at specific altitudes, creating a wall of shrapnel that enemy aircraft would fly through. The system required gunners to estimate the altitude and speed of incoming aircraft, calculate the time of flight for the shell, set the fuse mechanically before loading, and hope everything worked correctly. It rarely did. Of the 48 civilians killed at Pearl Harbor that day, most died when improperly fused. American anti-aircraft shells exploded on impact with the ground in downtown Honolulu instead of in the air near Japanese attackers. The shells that did explode at altitude rarely hit anything. The statistics from early war operations in the Pacific were catastrophic. Under good conditions, American anti-aircraft guns fired between 500 and 1,000 shells for every enemy aircraft destroyed. Under poor conditions, the ratio could exceed 2,000 shells per kill. That was not a defensive weapon. That was a waste of ammunition and a waste of lives. The Navy understood they had a fundamental problem. Modern aircraft were too fast, too maneuverable, and flew at altitudes that made accurate time fusing nearly impossible. Gunners needed a fuse that would automatically detonate when a shell came close to an enemy aircraft. They needed a proximity fuse. The concept was not new. Multiple nations had explored the idea for years. The British had working prototypes for rockets by 1940. The Germans had been researching proximity fuses since the early 1930s. Everyone understood the principle. Build a miniature radio transmitter into the nose of a shell. Have it emit radio waves continuously during flight. When those waves reflected off a nearby target, a receiver circuit would detect the strengthening signal and trigger a detonator. Simple concept. Extraordinarily difficult engineering. The National Defense Research Committee assigned the Proximity Fuse project to Section T of the Department of Terrestrial Magnetism at the Carnegie Institution in Washington. Section T was led by Dr. Merle Tuve, a physicist who had helped develop the theoretical foundations for radar in the 1920s. Tuve understood that the core technical challenge was not the concept, but the execution. Radio proximity fuses were conceptually simple. making them work in artillery shells that experienced acceleration forces 20,000 times greater than gravity, while spinning at 25,000 revolutions per minute, was the problem nobody had solved. Fuze assembled a team of physicists and engineers and gave them an impossible deadline. The Navy needed working proximity fuses for 5-inch anti-aircraft guns as soon as physically possible. Japanese air power was destroying American ships. Without an effective anti-aircraft defense, the Navy could not operate safely in the Pacific. Fuze's team had months, not years, to solve problems that had stumped British and German scientists for a decade. The team included some of the brightest minds in American physics and engineering. Richard Roberts and Henry Porter conducted experiments on circuit designs. Robert Broad worked on receiver sensitivity. Harry Diamond and Wilbur Hinman from the National Bureau of Standards developed fuse designs for rockets and bombs. The collaboration brought together academic researchers, government scientists, and industrial engineers in ways that had never been attempted before. Every member understood they were racing against time. American sailors were dying in the Pacific while they worked. The first breakthrough came from Lloyd Berkner, one of Fuze's engineers. Berkner developed a system using separate transmitter and receiver circuits instead of a combined transceiver. This simplified the electronics and made the system more reliable under combat conditions. But the vacuum tube problem remained completely unsolved. Standard vacuum tubes shattered under the acceleration forces of gunfire. The glass envelopes cracked during firing. The filaments broke from centrifugal forces. The tube elements came loose and destroyed the circuits during flight. Commercial vacuum tubes, even military-grade tubes, were designed to operate in radios, radar sets, and electronic equipment that experienced nothing more violent than being carried aboard ships or transported in trucks. Artillery shells were different. Artillery shells were subjected to forces that exceeded anything in civilian or military electronics. The solution came from an unexpected source. Western Electric Company and Raytheon manufactured miniature vacuum tubes for hearing aids. Hearing aid tubes were already ruggedized for portable use. They were small, mechanically robust, and used relatively little power. Working with Fuze's specifications, Western Electric and Raytheon engineers modified hearing aid tube designs to survive artillery gun firing. They reinforced the glass envelopes with thicker walls. They redesigned the filament mounts to prevent breakage under acceleration. They modified the internal structure to withstand centrifugal forces. They tested the tubes by firing them from air cannons into solid blocks of wood, subjecting them to acceleration forces far exceeding what they would experience in actual combat. Most tubes failed. The engineers redesigned them, tested again, failed again, redesigned again. By January 1942, after months of iterative testing and redesign, they had vacuum tubes that survived 20,000 G-forces and 25,000 RPM spin rates. The tubes were tiny, barely larger than a rifle cartridge. Each proximity fuse required 5 of these miniature tubes, along with resistors, capacitors, a battery, a safety mechanism, and a detonator, all packed into a space smaller than a beer can and weighing less than 2 pounds. The battery system alone presented enormous challenges. Standard batteries could not withstand the firing shock. The electrolyte would spill. The electrodes would short-circuit. The entire power system would fail within milliseconds of firing. Engineers developed a reserve battery that was activated by the setback force of firing. A small glass ampule containing electrolyte would shatter when the shell was fired, activating the battery. The liquid electrolyte would distribute throughout the battery cells due to centrifugal force, creating electrical current that powered the transmitter and receiver circuits. The safety mechanisms required equally innovative solutions. The fuse needed to remain completely inert during handling, transportation, and loading. It could not arm until the shell had traveled far enough from the gun to protect friendly forces. A premature detonation could kill the gun crew. Engineers designed a complex system using mercury switches that required centrifugal force from the shell's rotation to close, combined with a timer that ensured at least 0.3 of a second elapsed after firing before the fuse could detonate. This meant the shell had to travel at least 750 feet from the gun before it became active. Even if a shell misfired and fell near the gun crew, it would remain harmless. In early August 1942, the Navy conducted the first live-fire test of proximity-fused shells in the Chesapeake Bay. The cruiser USS Cleveland fired at radio-controlled drone aircraft on August 12th during its shakedown cruise. The test was scheduled for 2 days. It ended after 1 day because all the drones were destroyed. The gun crews aboard Cleveland fired 4 shells. 3 drones were destroyed. Navy observers present at the test were astonished by the results. The proximity fuses worked perfectly. For the first time in history, anti-aircraft gunners could reliably hit moving aerial targets without direct hits. The shells just needed to pass within 70 feet of the target, and the proximity fuse would detonate automatically, shredding the target with shrapnel. The improvement over time fused shells was so dramatic that some Navy officers initially suspected the test had been rigged or that the results were somehow misleading. But subsequent tests confirmed the initial findings. The proximity fuse represented a genuine breakthrough in anti-aircraft warfare. Successful testing and combat deployment were very different things. Fuze's team needed to scale up from prototype production to mass manufacturing. By January 1943, Section T had moved from the Carnegie Institution to a much larger facility and been reorganized as the Applied Physics Laboratory under Johns Hopkins University with Fuze as director. The project now involved 26 contractors and 10,000 workers. More than 100 American companies contributed to proximity fuse production, including General Electric, RCA, Raytheon, Sylvania, Westinghouse, Eastman Kodak, Zenith, Philco, and even Wurlitzer, the organ manufacturer. Each proximity fuse contained 130 miniaturized electronic components. Assembly required precision work. Workers at factories across America built these fuses without knowing what they were building. Security was absolute. The project had the same classification level as the Manhattan Project developing the atomic bomb. Workers who asked what the fuses were for were told only that they were critical to winning the war. Many workers never learned the truth until after the war ended. The Crosley Corporation in Cincinnati, Ohio, became one of the largest proximity fuse manufacturers, producing 5.2 million units, roughly 24% of total wartime production. The company converted its barrel organ factory into a fuse assembly line. General Electric's Christmas tree lamp factory in Cleveland was retooled to produce miniature vacuum tubes. Eastman Kodak, RCA, and Sylvania joined the production effort. At peak production, American factories were manufacturing more than 100,000 proximity fuses per week. The fuses that cost $732 each in early 1942 cost just $18 each by 1945. That price reduction reflected both improved manufacturing efficiency and the economies of scale that only American industry could achieve. In November 1942, the Navy shipped 5,000 proximity fuses to Pearl Harbor. The Pacific Fleet received 4,500 of them and began distributing them to ships operating in the Solomon Islands. But the fuses came with strict restrictions. They could only be used over open water where dud shells would sink to the ocean floor. If a fuse failed to detonate and fell on land, Japanese engineers might recover it and reverse engineer the technology. That risk was considered unacceptable. Pentagon officials feared that even a single dud shell falling into enemy hands could compromise Allied air superiority. On January 5, 1943, those restrictions were put to the test. The light cruiser USS Helena was operating off Cape Hunter on the south coast of Guadalcanal when Japanese dive bombers attacked. After dropping their bombs, the aircraft pulled up and began climbing away. Lieutenant Red Cochran commanded Helena's aft 5-inch battery. He ordered his gun crews to fire 3 salvos with proximity-fused shells at the departing aircraft. The gun crews had minimal time to aim. The aircraft was already several thousand feet away and climbing fast. All 3 shells exploded in the air near the dive bomber. The aircraft disintegrated and fell into the ocean. Helena's crew had achieved the first confirmed Kill of an enemy aircraft using a proximity-fused shell in combat. It was not a lucky hit. It was repeatable technology. Over the next 12 months, the effectiveness of proximity fuses in naval combat became undeniable. In 1943, Navy ships fired 9,128 proximity-fused rounds and destroyed 61 enemy aircraft. That was 1 kill for every 155 shells fired. The old-time fused shells required 508 rounds per kill. The proximity fuse was more than 3 times as effective. And this was just the beginning. As gun crews gained experience with the new fuses and fire control systems improved, the kill ratios got even better. By 1944, the number of proximity-fused rounds fired climbed to 32,826, accounting for hundreds of aircraft destroyed. During the Marianas Campaign, proximity-fused 5-inch shells provided critical air defense for carrier task forces operating deep in Japanese-controlled waters. During the Battle of the Philippine Sea in June 1944, American ships equipped with proximity fuses shot down numerous Japanese aircraft attempting to attack the carriers. The Japanese naval aviators, among the most experienced in their fleet, found themselves unable to penetrate the defensive screen created by proximity-fused anti-aircraft fire. One Navy study concluded that for every enemy plane destroyed, 5-inch guns had previously needed to fire approximately 1,000-time fused shells. With proximity fuses, that number dropped to about 250 shells per kill, a 4-fold improvement in effectiveness. On May 11, 1945, the destroyer USS Hugh W. Hadley was on radar picket duty off Okinawa when more than 100 Japanese aircraft attacked in a coordinated strike. Hadley's 5-inch guns were equipped with proximity fuses. In 90 minutes of continuous combat, Hadley shot down 23 aircraft, setting an all-time U.S. Navy record for a single engagement. Every proximity-fused shell that came within 70 feet of a target detonated automatically, filling the sky with lethal shrapnel patterns that aircraft could not avoid. The nearby destroyer USS Evans accounted for 19 additional aircraft before being forced to retire. Together, the 2 destroyers shot down more than 40 enemy aircraft. Both ships received Presidential Unit citations for this action. The after-action report described the proximity fuse as indispensable. While the Navy was using proximity fuses extensively in the Pacific, the Army was prohibited from using them over land in Europe. The restriction remained in place through 1943 and most of 1944. Army artillery officers knew proximity fuses existed. They had heard reports from the Pacific. They knew the technology worked. But Pentagon officials feared that even a single dud shell falling into German hands could compromise Allied air superiority. Germany had the most advanced scientific establishment of any Axis power. If German engineers reverse-engineered the proximity fuse, they might develop countermeasures that could blind Allied radar or create their own proximity-fused anti-aircraft shells that would devastate Allied bomber formations over Germany. The risk seemed too great. That calculation changed on June 12, 1944. Germany began launching Vone cruise missiles at London. The V-1s were jet-propelled flying bombs, pilotless aircraft packed with explosives and aimed at civilian targets. They flew low and fast, approaching speeds of 400 miles per hour. They were extremely difficult to intercept. Traditional anti-aircraft guns could rarely hit them because the V-1s were too small and too fast for accurate time fusing. British fighter pilots tried to shoot them down or tip their wings to send them off course, but it was dangerous work, and many pilots died attempting it. The V-1s killed tens of thousands of civilians and caused massive damage to London. The Pentagon authorized limited use of proximity fuses to defend London against the Vone attacks on June 12, 1944. Initially, the fuses were restricted to 90mm anti-aircraft guns and British 3.7-inch guns positioned along the English coast, where dud shells would fall into the ocean. The results were immediate and dramatic. In the first week of operations, British anti-aircraft guns destroyed 17% of incoming V-1s. This was already better than the 24% success rate achieved with traditional methods, including fighter interceptions and anti-aircraft fire combined. But as gun crews gained experience with the new fuses and fire control radars improved, the success rate climbed steadily. By the end of the fourth week, proximity-fused shells were accounting for 79% of all V-1s destroyed by anti-aircraft fire. By late August, after proximity fuses were widely deployed across the entire defensive belt, that percentage reached 74% of all incoming missiles. On some days, it reached 82%. The Germans launched 9,300 V-1s at England between June and August. Without proximity fuses, the casualties and destruction would have been catastrophic. The proximity fuse had saved London from what could have been an even more devastating assault. British Prime Minister Winston Churchill later called the proximity fuse potent against the small, unmanned aircraft and credited it with preventing far greater loss of life. When Vosne attacks shifted to the port of Antwerp in September 1944, the restrictions on proximity fuse use over land loosened further. Antwerp was critical for supplying Allied armies advancing into Germany. Losing the port would cripple the Allied offensive. The Germans recognized Antwerp's strategic importance and redirected their remaining Vosne launchers to target the city and port facilities. Between October 1944 and March 1945, the Germans launched more than 8,000 V-1s at Antwerp. British and American anti-aircraft units established defensive belts around the city. The British 11th Armoured Division defending Antwerp came under a particularly intense barrage in September that required emergency modifications to anti-aircraft fuses. The Crosley Corporation in Cincinnati worked around the clock to produce the specialized fuses needed. British Prime Minister Winston Churchill authorized a special flight of Lancaster bombers to transport the fuses from Cincinnati to Europe, demonstrating the critical importance attached to maintaining Antwerp's defenses. Once the modified proximity fuses were deployed, a single anti-aircraft unit in Antwerp destroyed 48 of the first 75 V-1s they encountered, a 64% success rate. With the Vosne threat largely mitigated, the port of Antwerp remained open for the duration of the war. By the end of the campaign, anti-aircraft units equipped with proximity fuses had destroyed more than 2,000 V-1s targeting Antwerp and London combined. On October 25, 1944, the combined Chiefs of Staff authorized general use of proximity fuses over land for anti-aircraft defense, formalizing what had become standard practice across the European theater. But ground artillery still could not use proximity fuses against enemy troops. Army artillery officers were furious. They knew proximity fuses would be devastatingly effective against ground targets. A conventional artillery shell detonated on impact with the ground, which meant that troops in trenches, foxholes, or behind cover were protected. But a shell that detonated in the air above them would spray shrapnel downward into their positions. Trenches became death traps. Foxholes offered no safety. Even log-reinforced bunkers could be penetrated by high-velocity fragments. Proximity-fused artillery would multiply the lethality of American firepower many times over. But the Pentagon held firm. The risk of a dud shell falling into German hands was still considered too high. Army artillery would have to wait. Then, at 05:30 on December 16, 1944, Germany launched Operation Watch on the Rhine. 3 German armies attacked through the Ardennes forest in Belgium and Luxembourg, hitting thinly held American positions with overwhelming force. The attack achieved complete surprise. German armour punched through American lines and began driving west toward the Meuse River and the Belgian port of Antwerp. The Battle of the Bulge had begun, and American forces were in serious trouble. Colonel Oscar Alfred Axelson stood in the fire direction center of the 406th Field Artillery Group near Monschau, Germany, listening to panicked radio calls from the 38th Cavalry Squadron. The lightly armed cavalry troopers were being overrun by German infantry. They needed artillery support immediately, or they would be annihilated. Axelson had exactly what they needed. Sitting in ammunition storage bunkers behind his position were crates of brand new artillery shells marked with red bands and the code name POSIT. These shells contained proximity fuses. Axelson made his decision within minutes of the attack beginning. His artillery group had just received shipments of POSIT shells. When the 38th Cavalry Squadron called for fire support, Axelson knew conventional shells would have limited effectiveness against German infantry advancing through forested terrain. But proximity-fused shells detonating above the trees would kill anything in the open. He ordered his gunners to load POSIT and fire. Using them without authorization could result in a court-martial, Supreme Commander. Dwight Eisenhower had not authorized their use, but the cavalry squadron was dying. Regulations could wait. The effect was immediate and devastating. German infantry caught in the barrage were cut down by airbursts they never saw coming. The shells detonated 30 feet above the ground. The German soldiers advancing on the 38th Cavalry Squadron suddenly found themselves engulfed in a steel rain of shrapnel falling from above. Foxholes offered no protection. Log-reinforced bunkers were penetrated by fragments. Men who had felt safe in covered positions were cut down by explosions they could not see coming. The German attack collapsed. 3 days later, on December 19th, General Dwight Eisenhower formally requested authorization to use proximity-fused artillery shells across the entire European theater. The German offensive was the largest attack the US Army had ever faced. Every advantage mattered. If you find this story engaging, please take a moment to subscribe. Enable notifications. It helps us continue producing in-depth content like this. On December 21st, all restrictions were lifted. Proximity-fused artillery shells were released for general use. The timing was critical. SS Colonel Otto Skorzeni's troops were attacking the town of Malmedy. American artillery battalions supporting Malmedy fired proximity fuses with devastating effect. The attacking German soldiers found themselves caught in airbursts that detonated overhead with no warning. Some Germans charged directly into the artillery fire, hands raised, screaming "Kamerad," the German word for comrade, trying to surrender. By December 23rd, estimates suggested as many as 2,000 German soldiers had been killed by proximity-fused artillery shells in just the first few days of their use. The Germans quickly realized they were facing a new type of weapon. Prisoners of war repeatedly described the demoralizing effect of artillery shells that exploded in the air above them with perfect timing. Traditional artillery gave soldiers a brief moment of hope. They would hear the whistle of incoming shells and dive for cover. If they were in a trench or foxhole, they might survive even a direct hit nearby because the explosion was on the surface. But proximity-fused shells detonated 30 to 50 feet in the air directly above defensive positions. There was no cover, there was no warning. The shells arrived silently at high velocity and detonated overhead, raining shrapnel straight down. Soldiers who had felt safe in prepared defensive positions were being killed without ever seeing the threat. The psychological impact was severe. German commanders offered rewards for any soldier who could recover an intact proximity fuse. They needed to understand how the weapon worked, so they could develop countermeasures or copy the technology. In late December 1944, German forces captured an American ammunition dump that contained 20,000 proximity-fused artillery shells. This was the moment Pentagon officials had feared for 3 years. German engineers now had access to the technology they had been ordered to prevent from falling into enemy hands at all costs. The captured shells were immediately transported to weapons testing facilities near Kummersdorf and other locations. German scientists began disassembling the fuses carefully, documenting every component. Dr. Engineer Hermann Riegner was among the first German scientists to examine the captured American proximity fuses in detail. What he found should have terrified Allied commanders. The fuses contained miniature vacuum tubes that had survived artillery firing. The circuits were more sophisticated than anything in German military electronics. The manufacturing precision exceeded German industrial capabilities. The Americans had solved engineering problems that German scientists had declared impossible. Riegner understood immediately what he was looking at. This was not theoretical physics. This was applied engineering at a level Germany could not match. But here is where the story takes an extraordinary turn. German engineers examined the captured fuses carefully. They recognized sophisticated electronics were involved. They could see the vacuum tubes. They could trace the circuits. They could identify the components. But they could not believe what they were seeing. German research teams had spent more than a decade trying to develop proximity fuses. More than 30 different designs had been explored. Acoustic fuses triggered by engine sounds, electrostatic fuses detecting field disturbances, radio fuses using various detection methods. Every approach had failed for the same reason. Vacuum tubes could not survive the acceleration forces of artillery gun firing. German scientists had tested this extensively. They had calculated the forces involved. They had designed reinforced tubes, modified filaments, and tried every engineering solution they could conceive. Every test ended the same way. The tubes shattered. In 1943, German engineers had reached a formal conclusion. Building a vacuum tube-based radio fuse for artillery shells was technologically impossible with current materials and manufacturing techniques. The acceleration forces would destroy the tubes. The problem could not be solved. So when German scientists examined the captured American proximity fuses in late December 1944, they faced a contradiction they could not resolve. Here were vacuum tubes that had obviously survived artillery firing. The shells had been fired from American guns, had flown thousands of meters while spinning at 25,000 revolutions per minute, and had either detonated or impacted the ground. Yet the tubes in the captured duds were intact. The glass envelopes were not cracked. The filaments were still connected. The internal elements showed no signs of catastrophic failure. This should not be possible. German engineers had two choices: accept that American manufacturing had achieved something German science had declared impossible, or conclude that these fuses were designed for a different application. Perhaps they were fuses for rockets, which experienced much lower acceleration. Perhaps they were experimental prototypes that had not been properly tested. Perhaps they were defective units that would not have worked in actual combat. The German engineers chose to believe the fuses were not what they appeared to be. This was not stupidity. This was not incompetence. This was the result of institutional knowledge and established scientific consensus telling them that what they were seeing could not exist. German proximity fuse research had been conducted by some of the best scientists and engineers in Europe. These were not amateurs. These were professionals who understood electronics, physics, and materials science. They had explored the same technical approaches the Americans had used. They had reached conclusions based on extensive testing and analysis. When confronted with evidence that contradicted their conclusions, they rationalized it away. The Americans must have used different materials. The tubes must be for lower acceleration applications. The technology must not work as reliably as it appeared. By the time German scientists understood they were wrong, the war was nearly over, and Germany had no industrial capacity left to develop countermeasures. This is one of the most extraordinary command and intelligence failures of the Second World War. Germany captured 20,000 American proximity fuses in December 1944. They had 4 months before the war ended. 4 months to analyze the technology, understand the principles, and develop responses. But they never recognized what they had captured because their own research had convinced them it was impossible. The Allies did not know this at the time. American intelligence officers believed the Germans would immediately understand the significance of the captured fuses. Within days of the ammunition dump being overrun, Allied scientists began developing electronic countermeasures. Winfield Salisbury, a physicist working on fuse development, designed a radio jammer specifically to interfere with proximity fuse circuits. 200 jammers were quickly constructed and installed in American bombers operating over Germany. The jammers were designed to emit radio signals that would prematurely detonate proximity, fused anti-aircraft shells, or prevent them from detonating at all. The jammers were never needed. The Germans never developed proximity, fused anti-aircraft shells because they never believed the American technology was real. On the night of December 25th and 26th, 1944, General George Patton's Third Army caught a German battalion attempting to cross the Sauer River near Echternach, Luxembourg. American artillery units fired a concentrated barrage using proximity-fused shells. The shells detonated above the river, and the German troops massed on the banks. There was no cover on the riverbank, no place to hide. The German soldiers were completely exposed in the open. Patton wrote a letter to the War Department describing the result. "The new shell with the funny fuse is devastating. We caught a German battalion which was trying to get across the Sauer River with a battalion concentration and killed by actual count 702. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad that you all thought of it first." 702 confirmed German dead in a single artillery barrage. That was unprecedented lethality. Conventional artillery shells might have killed 50 or 60 soldiers under similar circumstances. The proximity fuse had multiplied the effectiveness of American artillery by more than 10 times. And this was not an isolated incident. Throughout the Battle of the Bulge, proximity-fused artillery devastated German formations caught in the open. In the Hurtgen Forest, an American chief ordnance officer reported finding 96 bodies from a German patrol hit by a massed proximity-fused artillery barrage. "The bodies looked as if they had gone through a meat grinder," he wrote in his report. "The high-velocity artillery shells arrived too quickly for German soldiers to hear them coming. The air bursts detonated with no warning. Foxholes provided no protection. The shrapnel even penetrated log-reinforced bunkers that would have stopped conventional artillery. German units that tried to advance through artillery fire were annihilated. German commanders reported that their soldiers were refusing orders to move forward because they knew proximity-fused artillery could kill them, even in covered positions. Prisoners of war interviewed after capture described being in a dazed state after surviving proximity-fused barrages. They realized they were facing a new kind of artillery but could not understand how it worked or how to evade it. Minor mutinies broke out among German units that were ordered into areas known to be covered by American artillery. Some German soldiers simply refused to leave their bunkers when proximity-fused artillery was falling. The Germans had felt safe from traditional timed artillery because heavy overcast weather prevented accurate aerial observation. American forward observers could not see German positions clearly, which meant timed artillery shells would be set based on estimates that were often inaccurate. German troops had learned to take cover whenever they heard artillery fire and wait for the barrage to end. But proximity-fused shells did not require accurate observation. The fuses automatically detonated at the optimal height above ground, regardless of weather conditions or visibility. American gunners just needed to know the approximate location of German forces and fire. The proximity fuses did the rest. The bad weather that had protected German forces now meant nothing. By late January 1945, German resistance in the Ardennes had collapsed. The Battle of the Bulge was over. American forces had stopped the largest German offensive of the war and were preparing to cross the Rhine River into Germany. Proximity-fused artillery had played a critical role in that victory. Patton later stated that the funny fuse won the Battle of the Bulge for us. While that was an overstatement, the proximity fuse had undeniably changed the tactical situation. German forces that would have been able to defend prepared positions effectively against conventional artillery were wiped out by air bursts they could not avoid. Back in the laboratory near Kummersdorf, Dr. Engineer Hermann Riegner continued his analysis through January and February 1945. He had by now disassembled multiple captured fuses. He had documented every component. He had traced every circuit. He had measured every specification. His conclusion was unavoidable. The Americans had achieved a manufacturing breakthrough that exceeded German capabilities by a significant margin. The miniaturization alone was extraordinary. The vacuum tubes were smaller than anything in German military electronics, while being more robust. The circuit components were manufactured to tolerances that German industry struggled to achieve even in laboratory conditions. The battery system was elegantly designed, using centrifugal force from the shell's rotation to activate a reserve electrolyte system. The safety mechanisms were sophisticated, requiring both centrifugal force and time delay before the fuse could arm. This was not the work of a few brilliant scientists working in isolation. This was the product of industrial mobilization on a scale Germany could not match. Regner estimated that producing these fuses required coordination between dozens of manufacturers, precision machining capabilities across multiple industries, and quality control systems that could maintain specifications across millions of units. His report to the Army High Command in February 1945 was explicit. Germany could not replicate this technology in any time frame relevant to the current war. Even if German scientists fully understood the principles, even if German industry devoted all available resources to the project, even if there were no Allied bombing disrupting production, it would take at least 6 months to develop working prototypes and another year to achieve mass production. Germany did not have 6 months. The Eastern Front was collapsing. Soviet armies were approaching Berlin. American and British forces had crossed the Rhine. The war was lost. The proximity fuse had not decided the outcome by itself, but it represented something more important than any single weapon. It demonstrated the gap between American industrial capacity and German capabilities. On May 10, 1945, 3 days after Germany's unconditional surrender, American officers interrogated Reichsmarschall Hermann Göring at the Ritter School in Augsburg. General Karl Spaatz, commander of U.S. strategic air forces in Europe, led the interrogation. The questioning covered many topics: Luftwaffe operations, German jet fighter development, strategic decisions made by Hitler that had crippled German air power. Near the end of the 2-hour session, Spaatz asked a specific question: "Have you any knowledge of a proximity fuse?" Göring responded immediately: "Yes, in 3 or 4 months there would have been production." 3 or 4 months. Göring was claiming that Germany had been on the verge of developing its own proximity fuse when the war ended. This was technically true in the narrowest sense. German scientists understood the principles. They had working prototypes for rockets. They had research programs exploring various detection methods. But Göring's statement was fundamentally misleading. Germany had been 3 or 4 months away from proximity fuse production for more than 10 years. German research had begun in the early 1930s. Multiple programs had explored acoustic, electrostatic, and radio detection methods. Prototypes had been built. Patents had been issued. Research papers had been written. None of it had resulted in a deployable weapon because German industry could not solve the manufacturing problems. The Americans had solved those problems in 1941 and 1942. By 1943, proximity fuses were in mass production. By 1944, American factories were producing 100,000 fuses per week. By 1945, over 22 million fuses had been manufactured. Germany had captured 20,000 of these fuses in December 1944. German scientists had examined them in detail. They had documented the technology. They had written reports explaining how the fuses worked, and they had concluded that reproducing the technology was impossible with German manufacturing capabilities. Göring's claim that Germany was 3 or 4 months from production was either self-delusion or an attempt to minimize the extent of Germany's technological defeat. The truth was that Germany had been decisively outproduced and out-engineered by American industry. The proximity fuse was one example among many, but it was a particularly clear example because both nations had pursued the same goal, using the same basic approach, and only one nation had succeeded. Dr. Merle-Tuve never received significant public recognition for leading the development of the proximity fuse during the war. The project remained classified until after Japan surrendered. Even after the war ended, Tuve was reluctant to discuss his role. He understood that Section T had solved an engineering problem that saved thousands of Allied, quote, lives. But he also knew that many people at many organizations had contributed to that success. The proximity fuse was not the work of a single genius. It was the product of systematic collaboration between physicists, engineers, manufacturers, and military personnel across dozens of organizations. Over 22 million proximity fuses were produced during World War II by more than 100 manufacturers. That scale of production required contributions from thousands of people, most of whom never knew what they were building. After the war, Fuze returned to the Department of Terrestrial Magnetism at the Carnegie Institution and served as its director from 1946 to 1966. He continued research in geophysics and radio astronomy. In 1948, he was named an honorary commander of the Order of the British Empire for his service to the Allied cause during the war. President Harry Truman awarded him the Presidential Medal for Merit. But Fuze rarely spoke about the proximity fuse. When asked about his wartime work, he emphasized the collaborative nature of the project and the contributions of the engineers and technicians who had solved countless technical problems that made mass production possible. Dr. Merle Fuze died on May 20, 1982, at the age of 80. His obituaries mentioned his contributions to geophysics and his leadership of the Applied Physics Laboratory during World War II, but most did not detail the specific work he had done on proximity fuses. The technology had been declassified for decades, but it remained obscure outside military and technical circles. Fuze himself had never sought publicity for his wartime work. He believed that scientific achievement should be measured by results, not recognition. The proximity fuse had saved lives and helped win the war. That was what mattered. The Applied Physics Laboratory that Fuze founded continues to operate today as a research facility of Johns Hopkins University. It conducts work in national security, space exploration, and advanced technology development. The building in Silver Spring, Maryland, where Section T first assembled proximity fuses in 1942, no longer stands. It was demolished decades ago and replaced by commercial development. There is no memorial marker at the site. Nothing identifies it as the place where one of the war's most important technologies was born. The workers who assembled proximity fuses in factories across America went back to their peacetime jobs when the war ended. Most never learned exactly what they had been building. The soldiers and sailors who benefited from proximity-fused ammunition rarely knew the technical details of how the fuses worked. They just knew that anti-aircraft guns were suddenly much more effective and artillery barrages were far more lethal. The technology remained mysterious even to the people whose lives it saved. The 702 German soldiers killed by proximity, fused artillery on the banks of the Sauer River in December 1944 were buried in military cemeteries in Luxembourg and Germany. Their graves do not mention how they died. The military records list them as killed in action by artillery fire, which was true but incomplete. They were among the first ground troops anywhere to be killed by a technology that their own scientists had declared impossible. They died not knowing that the shells exploding above them contained miniature radar sets more sophisticated than anything Germany had been able to build. They died not knowing that American factories were producing these shells by the hundreds of thousands, while German industry struggled to manufacture basic artillery ammunition. The German engineers who had declared proximity fuses impossible never fully understood what they had missed. After the war, American technical intelligence teams interrogated German scientists and showed them captured German documents detailing their proximity fuse research. The Germans had explored most of the same technical approaches that Section T had used. They had considered radio frequency fuses, vacuum tube designs, and miniaturization techniques, but they had concluded that the engineering challenges could not be overcome with existing technology. What separated the American project from the German project was not a difference in scientific knowledge, but a difference in engineering persistence and manufacturing capability. American industry could produce miniature, ruggedized vacuum tubes in quantities of millions. American engineers could iterate through dozens of design failures until they found solutions that worked. Germany lacked the industrial base and the time to compete on those terms. British scientists who had contributed the initial circuit designs to Section T watched the American success with mixed feelings. They had solved many of the conceptual problems, but had been unable to scale up to mass production. The British proximity fuse program produced working prototypes, but never achieved the reliability and cost-effectiveness needed for large-scale military deployment. When the Tizard mission delivered British proximity fuse designs to Section T in August 1940, they gave the Americans a starting point. But as Fuze later noted, the circuit design that Section T made work was substantially different from the British design. American engineers had redesigned nearly every aspect of the fuse to meet Navy specifications and survive the brutal forces of artillery gun firing. This is how wars are actually won. Not through dramatic breakthroughs or genius inventors working in isolation, but through systematic collaboration between scientists, engineers, manufacturers, and military personnel. The proximity fuse succeeded because Section T could draw on the resources of American industry, the technical expertise of academic researchers, and the practical terminatory knowledge of Navy ordnance officers who understood what combat conditions would demand. It succeeded because Western Electric and Raytheon could manufacture ruggedized vacuum tubes that no one had built before. It succeeded because factory workers across America could assemble complex electronics at scales that would have been impossible for any other nation. And it succeeded because Colonel Oscar Alfred Axelson made the decision to use the technology when it mattered most, even though he was violating direct orders by doing so. The story of the proximity fuse is the story of American industrial and scientific power at its peak. It is the story of what becomes possible when brilliant people are given clear objectives, adequate resources, and freedom from bureaucratic constraints. It is the story of innovation that happens not through individual genius, but through systematic problem-solving at scale. And it is the story of a technology that saved thousands of Allied lives and changed warfare forever, developed by people whose names are mostly forgotten today. But perhaps most importantly, it is the story of what happens when established scientific consensus meets contradictory evidence and chooses not to see it. The German engineers who examined captured American proximity fuses in December 1944 had in their hands proof that their conclusions were wrong. They had vacuum tubes that had survived artillery firing. They had circuits that functioned after experiencing 20,000 G-forces. They had miniaturized electronics that exceeded anything in their own research. But they could not accept what they were seeing because accepting it would mean acknowledging that American engineering had surpassed German capabilities by such a margin that Germany could never catch up. So they rationalized it away. They convinced themselves the fuses were defective or designed for different applications or somehow not what they appeared to be. And by the time reality became undeniable, it was far too late to matter. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.